Today's lesson is 7.1, exponential functions. We're going to start off by looking at an application of exponential functions. Exponential functions are one of the most important and commonly applied functions that we see in Algebra 2. So we're looking at an article that I found on the internet. David Parrish is the author, and it's talking about exponential growth business model in the creative sector. So David Parrish did the research, and here's the link to the article if you want to look into that more. Looks like exponential growth is the aim of business worldwide, which makes sense. We've seen our exponential growth function and how quickly that rises in contrast to a linear growth model. The most powerful of all these business models is an exponential growth business model. These are quotes from this article. The most successful business in the digital industries have a scalable business model that allows them to grow exponentially. Unlike linear growth, which increases steadily, so linear growth has been the trend in business models, and it does grow steadily, and that's important. Growing steadily is valuable. But now exponential growth is rapid growth, for example, a doubling in size every 6 months. On a graph, linear growth is a straight line, whereas exponential growth curves upward. And here's just one example. So, you've probably heard of Hyatt hotels, and you've probably heard of Airbnb. So the Hotel Corporation Hyatt has 600 hotels worldwide. And that's at the time of the writing of this article, which I found just a year or so ago, so around 2018. And it has 10 different brands, and this means they have perhaps 15,000 rooms. And that's globally, available globally. And they have 95,000 employees. At the time of the writing, the corporation was worth $8.07 billion. And then there's Airbnb, a website for people to list, find, and rent lodging. It has over 1,500,000 listings in 34,000 cities in 190 countries. So you can see 1.5 million listings versus the 15,000 rooms here. At the time of writing, the company was worth $13 billion. Right, there's the contrast there. Furthermore, growth at Hyatt will be relatively slow, expensive, and linear. Its company is based on bricks. In contrast, growth at Airbnb will be rapid, inexpensive, and exponential. It's based on clicks. So there's your contrast of linear versus exponential growth and how that impacts the value of those businesses. Here's another example. We have Facebook. And you can see, and now this is, I'm sure, changed dramatically since 2015, but from 2007 to 2015, Facebook saw exponential growth. And you see that characteristic curve upward. Here's a second example. What is the graph of y equals 2 to the x? First of all, make a table of values. We'll start here at -3. We'll go to -2, -1, and 0. And then 1, 2, and 3. So we plug in a -3 into the exponent here. We get 2 to the -3rd power, which, recall, means 1 over 2 cubed, or 1/8. So that translates to the point -3, 1/8. So let's mark this graph a little bit further. This would be 1, here would be 1/2, 1/4, 1/8 would be very close to the x-axis there. And then 2 to the negative second power would be 1 over 2 squared, or 1 over 4, 1/4. Negative 2, 1/4. It's halfway between the x-axis and that 1/2 mark, and then 2 to the negative. First power is 1 over 2 to the first power, just 1/2. So negative 1, 1/2. 2 to the 0 power is, anything to the 0 power is 1. So at 0, we have our y-intercept of 1. Next we have 2 to the first power, or 2. So 1, 2. Then we have 2 to the second power, which is 4. So 2, 4. And then 2 to the third power, which is 2 times 2 times 2, or 8. So at 3, you're at 8. And you can see the curve there is increasing quickly. Exponential growth. So here are some definitions for us. We've looked at an application for exponential functions, another application, and then we've looked at an example of a graph. 2 types of exponential behavior. There's 2 types. We've looked at exponential growth. It increases rapidly. There's another type, exponential decay, and you've heard of that before, probably in science class. So exponential growth, we can define that as the value of x increases and the value of y increases. So that's your basic definition for exponential growth. And then exponential decay, as the value of x increases, the value of y decreases. So what we have in the picture here, exponential decay looks like rapid decline, whereas exponential growth is our rapid increase, right? Exponential growth, that's our purple curve here. Furthermore, when we are talking about exponential functions, we always have an asymptote. That's the way to say that, asymptote. It's a funny way to say that word. A line that a graph approaches as x or y increases in absolute value. So as this function increases in absolute value, so you can see the absolute value of x right here. Although it's negative, the absolute value would be positive, and it increases. It gets closer and closer to the x-axis. So the asymptote here, you can see, is the x-axis, and each one of these functions gets closer and closer to that value. Put a big old star next to this next thought. In the function y equals ab to the x power. That's a general expression for exponential function. If a is greater than 0 and b is greater than 1 in this expression, we know we have exponential growth. If a is greater than 0, notice that's the case in both of these. A needs to be greater than 0. And b is between 0 and 1. The function represents exponential decay, right? Just like we saw over here. So that would be a fraction or a decimal between 0 and 1 for the b value. That's this value right here. That helps us to know whether or not our graph will be exponential growth or decay. In either case, so regardless of growth or decay, we have a y-intercept at a comma 0. So that value right here in front is going to indicate our y-intercept. The domain is all real numbers, and the asymptote is y equals 0, and the range is y is greater than 0. So let's take a look at a couple more examples. Here, determine if the function represents exponential growth or decay, so that's the first thing we need to do. And the second thing we need to do is identify the y-intercept. For the first instruction determining exponential growth or decay, we're looking at the b value. Remember, that's the one that's raised to the power. So here, our b value is 0.95, and that is between 0 and 1. So that's going to represent decay. And then the next thing we're looking for is the y-intercept, and now we're looking at the a value. So that would be the thing not raised to a power prior to the value that is raised to a power, so that's a equals 12. So our y-intercept is 0, 12. And just these couple values help us to have an idea on what the graph of this exponential function would look like. We can imagine a y-intercept of 0, 12, somewhere up here, and exponential decay. So we're taking a look and kind of imagining what these graphs would look like by simply being able to identify the key pieces to this function. Letter b. First of all, we're looking at the b value. That's the one raised to the power. b is 2. That is greater than 1, so that's going to represent exponential growth. Next, we look at the value in front, and that is a equals 0.25, helping us to determine that our y-intercept is 0.25. So we can imagine the value right in here for our y-intercept and an exponential growth. Letter C is tricky. The thing you need to know is that the b value is always raised to the power. So this 6 is our b value, helping us to see that this is greater than 1. It is a growth function. Our a value is the thing in front of that. Since there isn't something, we can fill in a phantom 1. So a is 1. And this is a very common a value. So 0, 1 is the y-intercept. Last example, D. We have y equals 0.75. I should start with my b values, it can be consistent. B values 4, greater than 1, that's a growth function. And my a value is 0.75. So that means my y-intercept is 0 and 0.75. Lastly, we'll take another look at an application. A common application of exponential functions is discussing our investments, our financial investments. So if we put $1,000 into a college savings account for 4 years, the account...
Excuse me. Good morning, Amanda Roberts. If you're in the building, come to the office, please. Thank you.
pays 5% annually interest. So you can model exponential. I'm going to answer that in just a second as we take a look at this function. Growth or decay with this function. And we'll talk more about functions in our next unit. This is called function notation. A of t equals a times the quantity 1 plus r to the t power. And each one of these is labeled nicely. So we can go back and fill in this scenario. So $1,000 is my initial investment, and that's lowercase a. So we'll put that here. And 1 plus my rate. Now my rate R here is 5%. We always want to write that as a decimal. So that's going to be 0.05. And then for the t time, they tell me 4 years. So we're going to raise that to the 4th power. So the thing we're solving for is a of t, or how much we'll have after 4 years. So we can enter that into the calculator. 1,000 times 1, I can add 1.05. 1.05 raised to the 4th power. And you can see here the a value, the b value, and then the x value. And then I have my final amount is $1,215, and we'll round to 51 cents. One more example, similar. You've invested $1,000, and so we'll set this up in the same way. The account pays 5% interest. So this is the same scenario. However, the thing that's changing is the time. T is now 6. So 1,000 times 1.05 to the 6th power. I can actually go back and retrieve this function and just change my 4 to a 6. And we wind up with $1,340, and we'll round that to 10 cents. Again, you can see from our initial investment was $1,000. After 4 years, we had $1,215, and then after 2 more years, 6 years, we have $1,340. So you have that rapid increase in your investment. And that is exponential